Always go right. My name is Manuel Kraemer. I work with NVIDIA. I'm sure you know we make GPUs. You probably have one of ours working on your workstations or gaming PCs. And tonight we're going to present you some of the work we've been doing to try to make VR immersion and VR experiences more comfortable and more impressive and more engaging with our audiences. So our main focus, of course, of VR is trying to convince our users that they're in a world that does not exist, and we have to work with all their senses. We have to convince them that through sight, sound, and touch as well, that really what surrounds them is the world that they're in. And the more convincing we can be, the more engaging the experience, hopefully, and the more interesting the VR application is. And finally, as a last little addendum to this presentation, we have also a few little tidbits on capturing the real world, because once again, this is not just about synthetic worlds. We also want to actually be able to use the real world that we live in, and there's some interesting work going on there as well. So as far as NVIDIA is concerned, most of our tools and solutions revolve around what we call VRWorks. VRWorks is a set of SDKs and API. And our goal is to try to really bring reality to VR, to really sort of enhance the performance, enhance the quality, and enhance the freedom that as a developer you can have to produce a great application. So as you can see, we have a number of different SDKs. They all target very particular areas. They're all very specific in the functionality. Some are dedicated to graphics. Some are dedicated to HMD manufacturers like Oculus here. To try to interface better with the hardware. Some are dedicated to haptics, and further on, video, audio. All of these have particular demands, and we're trying to address some of these challenges everywhere as best as we can. So today I'm going to explore some of these solutions, obviously not all of them because we only have 20 minutes. And hopefully this will have interesting bits for everyone working on VR and have solutions for problems that you may be facing. I will start with graphics because that's probably where we have the most challenges right now. We all know that it's difficult to get applications to look great. It's difficult to have them perform. And graphics is really where we're in the trenches at the moment with VR. And that's probably one of the biggest topics today. So what are the main challenges? And there's many of them. Obviously, the first one is latency. That's probably the most exacting and demanding challenge of VR. It's been sort of established a while back that about 20 milliseconds motion to photons is roughly the point where humans start feeling comfortable. And if anywhere above this, we start experiencing motion sickness, proprioception, and so on and so forth, which means people are unhappy and generally will not want to keep the HMD on their face. So trying to improve motion to photon, oh, by the way, motion to photon is what we generally call the time elapsed between the moment where you move your head and the image is being updated in HMD. So essentially, time from the movement of your head all the way down to your headset. The problem with this is 20 milliseconds is not a whole lot of time, and we have a pretty long pipeline to actually go through. It starts first on the HMD side, of course. We have to capture the position of the head, to capture the position of your hand trackers if you're using touch, for instance. And already that takes some time. Then it goes through the CPU, it's getting processed. The CPU makes a number of decisions, run the game engine, the AI, everything else, and start queuing the graphics works on the GPU. Then the GPU does the heavy lifting over there, produces an image, but the image has, again, to be sent to the actual head-mounted display. So when everything is said and told, you actually spend, out of the sort of 20 millisecond budget, what you have left is about 11 milliseconds for both your CPU and GPU work. 11 milliseconds is really not a lot of time to get anything done. And of course, you can split it any way you want, more on graphics and more on the CPU. But overall, like I said, if you look in terms of regular sort of video game engines, 11 to 12 milliseconds is really a very short amount of time to get anything significant done. So that's the first challenge, and it's a pretty big one. The second challenge, of course, is this is not a traditional desktop game title. So if you look at your console, you're playing, I don't know, Halo or some other game on your TV, what you're usually working with is a resolution of 1080p, and so you play at 30 frames per second. I know the gaming purists over here are going to be howling at me, but Let's say for the sake of argument, this is what happens in modern graphics. That means that you would be rendering at roughly 60 million pixels per second. That's the current load that you're putting on your GPU every second. For VR, first, the screen is a higher resolution. I've got numbers over here on the right, don't get too attached to them, but that's roughly what's modern to the Rift, the Vive, and other displays that you find for desktops. But you're also not rendering at 30 frames per second. You're most importantly rendering at 90 frames per second to hit, again, this sort of 20 millisecond latency kind of issue. And if you do this, if you render this resolution and frame rate, this is not 60 million pixels, it's 450 million pixels per second that you have to provide to the head-mounted display. So that's roughly an 8x increase in computation power. I wish I could give you tomorrow a GPU that is 8 times faster. Reality, unfortunately, doesn't work quite that easily. So the point I'm trying to make here is we're going to have to render smarter, obviously. We don't want to give up the quality of our graphics. We don't want things to look like Tomb Raider in 1995, or sorry, that was 1999. We want things to look like modern, engaging, great-looking visual experiences, great-looking games, or great-looking experiences, but we just do not have the render power. So how can we do things smarter? So I'm going to geek out for a second on HMD optics. I'm sure this is things that you've already seen many, many times around, but bear with me just for the repetition a little bit. What you see, what is actually displayed on the HMD display, the vignette on the left, is an image that's been already warped. Why? Because there is a whole chain of optics. There's a bunch of lenses in the head-mounted display that goes between your eyeballs and the screen. Those lenses, as you can see in the vignette in the middle, they distort the image, they warp it. And of course, the image that you see on the right is what you want to perceive. Ideally, that's the undistorted scene that surrounds you. So putting this in context, this means that the image that I render on the left, which is ultimately what I want my audience to actually perceive and see, is not the image that the actual display really cares about. The image that the head-mounted display uses is a warped version of this, which means that once I have run my game engine, I've produced the image on the left, the HMD driver comes in and applies a warping operation to the image to produce the image on the right. And if you look at the image on the right, you can see that there's a whole lot of work that's already not really going anywhere. Put more bluntly over here, if I define two areas, the area in green towards the center, as you can see, is mostly unchanged through this warp. However, the areas on the sides, as you can see, they get squished a lot, which means that out of all the pixels I rendered on the image on the left, many, many of these pixels, a significant percentage, never makes it to the image on the right. They're simply discarded in the warp operation. So this is a whole lot of computing power that we're spending that is not being useful. In other words, we're wasting time and we're wasting latency. So in order to fix this, one of the early solutions that NVIDIA came up with around Maxwell-era GPUs, that's what, 2 years ago already, an eternity, was what we call multi-res shading, or multi-resolution shading. So we're basically deciding to arbitrarily split the screen into 9 areas, and we're going to render each one of these with a different resolution of pixels. So the area in the center is obviously the one where you want the most details, because that's the one that's less warped. But the areas on the side, we can render at half resolution or even at a quarter resolution in the corners. And we can put this all back together. And this was mostly made possible through a little hardware feature that was added with Maxwell, which basically says, if you feed me one triangle through the geometry pipeline, I can actually distribute it at the same time in all the different viewports, which means that the work that the GPU does to process the geometry is only done once for all the viewports at a time. Otherwise, if you didn't have this feature, you basically would have to tell the GPU, draw the image or draw the whole scene for the first tile, then draw the whole scene for the second tile for each tile that you've got, which would be 9 times the amount of geometry processing. Here, we just do it once, and we reuse it for every one of the viewports. It's a pretty powerful idea. You actually process, or you actually queue the render command once, and it magically sort of renders in 9 different separate viewports, and you only pay for one geometry processing stage. So that was the idea back then. There's been a few refinements since, though. So the first one was, well, rather than just separate the screen in 9, which sort of gives 9 arbitrary, discrete, different rates of pixels, which can show discontinuities, and it's kind of hard to work with, it would be nice if actually what we rendered matched more closely the actual geometry of what the lens does. So instead of doing multi-res shading with Pascal, we extended this little hardware feature, and we essentially extended the technique, and we called it after that lens match shading, because it's closer to what really happens inside the lens. So instead of rendering the image of the back on a flat plane and split it in 9 regions like MRS does, what we did is we actually split it into 4 areas, but now they're canted in depth. And you can see that the surface that we're actually rendering starts looking closely to what the lens does in terms of warp in the actual HMD operation. So this was a refinement and an improvement on the original technique. But of course, we can extend this idea of broadcasting geometry even further. If you render for VR, of course, you have to render the left eye and the right eye. This would be 2 passes. So in other words, you have to first tell the GPU, render all the scene for the left eye, then render all the scene for the right eye. And that's, of course, duplication of work again. With the idea of simultaneous multi-projection again, and LMS, you can combine everything. You can say one single call, and you draw all the tiles at once, and you render both the left and the right eye. So again, you pay for the geometry computations only once, but reuse them for all these tiles, and you get a much more fitting image to the warp that's produced on the end. So again, trying to sort of save a lot of work that can be reused across all these different images that are very similar. So of course, you're still going to hit cases where this is not going to be enough. So when you're talking about GPUs, one feature that's been very often used is SLI. In other words, pairing multiple GPUs to produce more computation work at a given frame rate. And with VR, of course, we have another opportunity once again to improve on existing technology. So of course, SLI predates VR, but there's ways to make it better. And the obvious one over here is we can actually use GPUs to render the image for the left and the right eye at the same time. Why is this important, or how is this different? Well, I'll geek out on this very quickly, and I'll hopefully convey how this works. Normal SLI is what we call AFR SLI, or alternate frame rate. In other words, each GPU renders a different frame at a different moment in time. So the GPU 0, for instance, starts at a given time, renders frame n, while the second GPU renders the frame after that, frame n plus 1. But that frame usually starts halfway when the first frame is completed, because we want to make sure that the frame rate stays consistent over time so you don't see stutters. The problem with this, of course, is because we now have these half-frame delays with AFR, you get a half-frame worth of latency at the end of the process. And of course, latency is the enemy of VR. So in order to avoid this, what we can do with VR SLI, and the main difference over here is we queue both frames at the same time on each GPU, so that when they complete, we can save essentially half a frame's worth of rendering time in latency. So it's a very minor distinction, but again, it helps, and it was a small adaptation we could do to existing solutions to make, again, our hardware better suited for VR. So when you put all this together, LMS, single pass stereo, and VR SLI and everything else, you actually end up in a situation where you can actually visualize very, very large data sets at interactive frame rates in VR. This is an example, for instance, over here of a CAD model which has 155 million triangles that currently can be rendered at 90 frames per second in an Oculus HMD headset. So just to wrap this all up with the graphics section, and I'm going to go very quickly because time flies by. All these features have been integrated in main leading game engines. So if you work with Unity, you will find multi-res, lens match shading, single pass stereo VR SLI in the latest Unity releases. And of course, you can download the plugins. I'll leave the links over here. We also have integrated the same feature set in Unreal. So again, if you work with Unreal, here is the contact information available from releases 4.12 to 4.16, I believe 17 actually. These slides are outdated, I think 4.17 is out already and supported. So again, if you work with these great game engines, have at it. You can use all these features and try to make your application faster. That was it for graphics. I'm going to go very quickly and briefly through audio because we've also have a few solutions in that area. So of course, your perception of your environment depends very heavily on what you hear. Immersion is not just sight, it is sound as well. If you're sitting in an elevator, sound does not sound, or you don't perceive sound in the same way as what you would in a symphony hall or outdoors. Things, you can instantly tell whether in a small area or in a wide area. And the reason for this is because there's mostly three aspects in simulating sound. And the first one, of course, is synthesis. You got to produce the sound. That's pretty obvious and easy. We've been doing this for decades. The second one was directionality. Direction in sound is sort of reasonably easy to accomplish in the sense that, with stereo, for instance, you can tell what's on your left and on your right. We've added channels, 5.1 Dolby, and so on and so forth. You get a pretty good idea of where sound comes from. What is more complicated, however, is propagation. As in sound propagates through a volume and bounces everywhere, but your brain is very tuned to how these bounces happen to tell you what kind of environment you're in. You can tell whether you're standing next to a pillar, for instance, in a parking lot, because you can feel the bounces of the sound around you and the absence from that area where the pillar is, for instance. So I had a little video over here. Unfortunately, I think we're facing some difficulties and they won't play. Let's see. That's a little scary. So I'll just pretend that this video is playing here, but the idea is here, when the sound source, of course, emits some signal, the signal bounces all around you, and you need to track this. And if this sounds like a sort of global illumination or ray tracing problem, you're actually entirely right, because the solution, VRWorks Audio in this case, does exactly that. It models the propagations of sound by ray tracing the environment around you and tries to provide a mix that is specific to your location, including the bounce and propagation of the sound around you. So this is pretty revolutionary, and it does make a pretty big difference in how you perceive the soundscape around you. So I'm running low on time. I'm going to have to pick up the pace, unfortunately. Another aspect of VRWorks and general tools that we have in our toolbox, of course, is physics and touch. So again, immersion, proprioception, and everything else means that if I'm interacting with controllers, I have to be able to detect collisions and have to be able to translate reactions on the environment to these collisions. So in other words, if I try to grasp something, if I try to knock something over, all these things are complex physics problems. They all have to be solved interactively, really fast, but also really accurately, because if it doesn't work, you'll very quickly feel that the world around you just does not work like you would expect it to work. It all has to be very intuitive. So for this physical simulation, we actually can leverage a lot of the work that NVIDIA has been doing in the area of gaming. Since we've actually been providing middleware for gaming titles for a very long time, we have solutions for many, many of these problems. We can simulate rigid bodies physics. We can simulate fluids, destructions blowing things up, hair, flow, cloth. All these are sort of similar kind of problems. And they all sort of have some level of support or solution within physics and VRWorks plugins and modules. So I had another video here of Funhouse, which if you haven't seen yet, I think that I don't really need to belabor this. But again, this is the kind of innovation that we're trying to bring to VR to really sort of put you in the middle of a world that you can believe reacts to your interactions and reacts to you being there. So if you knock something over, that thing will keep on rolling and knocking other things around as, again, the physical properties of the object dictate. And finally, I've got about 2 minutes to wrap this up. Again, VR, we're seeing a lot of synthetic things, but we also see emergence of capture of real world. We want to actually put you in existing live environments being streamed. So we have we've been working on solutions there as well. There's a number of interesting computational challenges in that area. And it started at SIGGRAPH in 2016, where we started seeing a lot of rigs trying to capture 360-degree video footage at pretty high resolution and pretty high frame rate. And in 2017, we actually partnered with Zcam and their piece of hardware to produce a 360 stereo SDK. So if you have an array of cameras with fisheye lenses, you all know that you need to stitch all these inputs into a panoramic video image at high resolution, high frame rate, without artifacts. You don't want to see any seams. You don't want to see any tone mapping errors. It's a pretty hard problem, and it's an even harder problem to do live. So VRWorks 360, the stereo SDK, like I said, provides an online and offline solution to render stereo and mono panoramas, EchoRect as we call them. And It supports a variety of rigs, and particularly the Z-Cam that I was just showing before, and also has encoding, decoding of video, obviously, stitching, equalization, calibration. All these things are handled in a pretty much turnkey solution. So if you haven't seen the demos yet, by the way, they're pretty cool. And I really wish I had that video playing. The final little project that we've been working on recently is Holodeck, which has actually been unveiled and announced in more details just this week, in fact. I'll again have to sort of pretend I can simulate the video here. Holodeck is basically a virtual collaborative environment. It is not oriented for gaming, it's oriented for professional collaborations, and the key point over here is that you can interact with extremely detailed models. In this particular case that we showed at SIGGRAPH, this is the Koenigsegg supercar, and this is the entire CAD model, as in every single nut and bolt. And if you press a button, it magically explodes in all these pieces. And the interesting part of Holodeck is, like I said, it's a collaborative environment, which means that different users can connect from anywhere in the world and all share the same experience, and they can all interact with this model. So you can actually review, take notes, give notes, and like I said, collaborate in this virtual space. And that's where, again, the ability of providing photorealistic, amazing graphics at interactive rates in VR is absolutely stunning. So if you haven't seen Holodeck, hopefully, I'll try to see if I can play the video in the next few minutes after we are over. But it's definitely worth a quick look. And I believe on the dot, I am out of time. So thank you very much. If there's any questions.